So now that you are familiar with HDL and hardware simulation, we are ready to get our hands dirty and actually go and develop some chips. So in this unit, we're going to give you all the information that you need in order to design the chips that we have to build in Project One. Before we go on, let us remind ourselves what is the general spirit of this course. Well, the story that we're telling you is that God told us, here's a logic gate, NAND, now go and build a computer. And when we asked, how can we possibly do that? God said, one step at a time. And in particular, the hack computer that we are going to build in this course consists of something like 30 different chips, and we are going to build them one step at a time. And in the first project, we start with NAND, which is God-given or given by us, or you can think about it as some sort of an axiom that you can assume. And using NAND, we want you to build the following gates: NOT, AND, OR, XOR, and so on and so forth. So that's what you have to do for Project One. And why these particular 15 gates? That's a good thing to ask. And the answer is twofold. First of all, every one of these gates is widely used in almost any construction of a digital device or some version of these gates. And the second answer, which is more practical, is that these gates comprise all the elementary logic gates which are needed in order to build our computer. So Project One lays out the foundation that we're going to use in subsequent projects, because in other projects we're going to use these chips in order to build more complex and more interesting functionality. So once again, here are the chips that we have to build, and I have separated them into three categories, just that we can discuss it in a more organized fashion. So we have some elementary logic gates, widely familiar, NOT, AND, OR, and so on. We have 16-bit variants of some of the logic gates, and we have some multi-way and also multi-way 16-bit variants of the previous gates. And in order to make this all these new concepts more familiar, I will focus on some gates in every one of these categories and say a few words about them. And this, once again, will give you everything that you need in order to build any one of the gates in Project One. So without further ado, let's start to talk about multiplexers and demultiplexers. So what is a multiplexer? A multiplexer is a gate that operates as follows. There are two inputs coming in, and we denote them A and B, and there's a cell input coming in, so-called, from the bottom. Of course, in reality, there's no bottom and left, but I'm talking about this gate diagram here. So three inputs come in, A, B, and cell. What does the multiplexer do? Well, if cell equals 0, the multiplexer outputs A. If cell equals 1, the multiplexer outputs B. That's it. That's the desired behavior of a multiplexer. And here is the truth table of the multiplexer. We have three inputs, so we have 8 different possibilities. And you can convince yourself that the truth table is consistent with what we described before. We can also provide an abbreviated truth table of the multiplexer operation. Once again, if cell is 0, the multiplexer outputs A, otherwise it outputs B. So a two-way multiplexer enables us to select and output one out of two incoming inputs. And this is a fundamental operation that is being used over and over again, both in digital design projects as well as in communications networks. So here's an example of how MUX logic comes to play in the context of building what is sometimes called a programmable gate. Now, what is a programmable gate? It's a gate that can behave in one of several different ways according to our will. So here's a simple programmable gate that can act either as an AND gate or as an OR gate. If the select bit is 0, the gate acts as AND. If the select bit is 1, the gate acts as OR. And here's the truth table of the gate, and you can convince yourself that it's consistent with what I said earlier. And here is how I can actually build it. I can use two gates, an AND and an OR, provided, of course, that I have developed them previously. And I can feed the A and B inputs simultaneously to both AND and OR. And we called this before fanning out. So the A input is fanned out into both AND and OR, and the same treatment is done with the B signal. And then I use a single multiplexer to decide, if I want to output the result of the AND or the result of the OR. So the user of this gate that sees only the interface of the gate gets exactly what he or she wanted, a programmable gate. Here's the HDL code that implements this particular architecture. And if you want, you can stop the video and inspect this code and make sure that it's consistent with the gate diagram. So here's an example of a MOOCs in the context of a digital design application. How do we build a multiplexer? Well, we get all this information from the system architect, and we also get a stub file. And what we have to do, of course, is to write the HDL code. And it turns out that we can build a multiplexer using 3 gates, AND, OR, and NOT, which we wire in a certain clever way, and the result is the desired MOOCs logic. So it's up to you to figure out how to do the wiring and actually implement the desired multiplexer. All right, moving along, let us talk about demultiplexer. A demultiplexer looks like the inverse of a multiplexer. It receives a single input, and based on the selection bit, it either channels the input to an A output or to a B output. Okay, so it's kind of a distributor of a value into one of several possible channels. In this example, we have it's a 2-way multiplexer, so it's a relatively simple example. All the other channels get 0. Okay, and so the DMUX is basically an inverse of a MUX. A DMUX is an inverse of a MUX, if you don't like my pronunciation. And once again, it distributes a single input into one of several possible output channels. Once again, just like we said about, what we said about the multiplexer, demultiplexing is also something which is widely used in digital design projects as well as in communication networks. And we're going to get, or you are going to get the stub file, and you actually have to implement the logic in HDL. All right, I'd like to give you an example of how multiplexing and demultiplexing can come to play in the context of communications networks. So here's a typical situation in building a network. And the situation is such that we may have several channels coming in, let's say channels of music or several movies that we want to send over a single communications line. So the single line that goes here in the middle of the slide can be 5,000 kilometers long. And it may be sort of an underwater line or a satellite line. And through this single line, I want to send multiple messages. How can I possibly do it? Well, if everything is digital, I can put a MOOCs in the sending end of our story, and I can feed the MOOCs an ongoing train of 0, 1, 0, 1, 0, 1, 0, 1. This can be done using what is known as an oscillator. And because the MUX is going to get a repetitive train of 0, 1, 0, 1, it is going to output blue, red, blue, red, blue, red. In every cycle, the MUX will output, one bit from one of the two inputs. At the receiving end of this story, once again I put a different oscillator, and therefore the DMUX is going to distribute the incoming inputs according to the DMUX logic. It will output blue, red, blue, red, blue, red, blue, red, and so on. So this logic here, the DMUX and the MUX logic taken together, enable me to braid or interleave several messages over a single communications line, which may be very expensive, and therefore it pays off to use it for multiple messages. And by the way, another attractive thing about this scheme here is that it can be completely asynchronous, right? They don't have to operate according to a master clock. Every one of these two operations, the encoding and the decoding operations, can be done separately. All right, so we talked about MUX and DMUX, which were by far the most complicated chips in the elementary logic gates that you have to build. And let's go on and talk about one example of out of the 4 16-bit chips that you have to build. So we'll talk about N16. And N16 looks as follows. We have 2 inputs coming in. Both of them are 16-bit buses, and we have a single 16-bit bus coming out. And basically what we have to implement is a 16-bit AND operation. So it looks like this, right? 1 and 0 should give us 0, 0 and 0 is 0, 1 and 1 finally gives us 1, and so on and so forth. We're going to get 1 if and only if both inputs are 1 in the respective index that we are looking at. Now there's something which is a little bit deceiving in this example here, because the calculation of the logic here is not sequential. Everything is being outputted, boom, in parallel. And this also gives you some tip on how to actually build it, okay? This is a straightforward extension of elementary AND gates. You can read more if you want about how to handle buses of data in HDL. And basically, once you get this stub file, we can implement an AND gate using a set of two-way AND gates. All right, so this has been what I wanted to say about the 16-bit variants that you have to implement. And finally, I want to discuss one example of the multi-way variants, which happens to be actually quite a straightforward notion. Here's an example of a MUX 4-way 16. It has 4 inputs coming in. Every one of them is a 16-bit bus. We have a 2-bit selection coming in, and that is because you need 2 bits in order to select 4 different possibilities. And we have the stub file, and we can build this thing using several MUX 16 gates, as well as perhaps some other gates as needed. So what do we have to do in project 1? Once again, we have to implement all these gates, starting with nothing more than NAND and previously designed gates. So, once you built NOT, you're welcome to use it. Once you built NOT and AND, you're welcome to use any one of these 2 gates, and so on and so forth. So how do we actually do it? How do we actually build every one of these gates? Well, we're going to give you some building materials, and we're going to use XOR as an example. So, you have the gate diagrams from the book or from the lecture. We're going to give you this HDL file, which is available to you, and you can open it up in a text editor. And we're also going to give you a test script and a compare file. And here is the contract that we want you to to play with or to play by the rules of this contract. When you run your XOR HDL, that is, once you take this XOR file and implement it and add your own HDL, when you run the resulting XOR HDL file on the supplied XOR test, the test that we provide, your output file should be the same as the supplied compare file. If this will happen, you have built the chip to our satisfaction. Once again, if your chip generates the expected behavior that we have specified, then you are done with this chip and you can go on to develop the next one. So for every chip that you have to develop, we're going to give you stub file, test script, and a compare file. All right, so the resources of Project One are listed in the NAND to Tetris website. You can look at the different files if you want. And there's no need to download anything, because if you've downloaded the course software suite, then all the necessary files that you need for this project are available in your projects /01 directory, and you're welcome to start working with these files and build Project One. If you need some additional resources, you can look at what we did in the first week, just to sort of get you warmed up for this project. There is the HDL Survival Guide, tutorial, and the Q&A forum. You can consult with any of these resources in order to gain some confidence and actually go out and build Project One. In closing, I would like to say a few words about what we call the Hack Chipset API. When you build a particular gate diagram like this one, you're going to use all sorts of chip parts. In this case, 2 AND gates, a single OR gate, and 2 converters, or 2 NOT gates. And the question is, how are you supposed to know what are the names of the input and output files, the input and output pins of every one of the gates that you want to use? Well, the answer is that if the gates that you use are so-called off-the-shelf gates, or if they are part of the Hack Chipset API, we provide all the necessary information about how to use them. And in particular, there is a document on the NAND to Tetris website that gives you the API of all the chips in the Hack chipset. This document is actually part of the HDL Survival Guide. So whenever you're not sure, what are the names of the inputs and outputs pins of a particular chip part, please consult this document and you will know how to use them. Another thing that I'd like to say in closing, before we end this unit, is that you can always use what we call built-in chips. For example, suppose you implement some chip called foo, and you want to use a chip part called bar. How can you do it if you haven't written bar before? Sounds a little bit impossible, but in fact, it is possible. So once again, if you don't implement some chips that are part of the chip of the Hack chipset, you can still use them as chip parts. All you have to do, if we gave you the stub file of bar, you have to change the name of this file to something else. For example, instead of calling it chipname.hdl, you can rename it chipname.hdl1. Once you do this, when you load foo into the hardware simulator, the simulator will look for an HDL file that corresponds to the missing chip part, and if it will not find it, it will by default revert to using the built-in implementation of the missing chip. So this gives us tremendous flexibility, because it means that in principle we can build these chips in any order that we please, although we recommend that you build the chips in the given order that they are listed in Project One. So here are some general best practice advice for project 1 and for subsequent projects as well. Once again, we recommend that you build the chips in a given order because they are specified from the simpler to the more complex. If you don't implement something, you can put it aside and if you want, get back to it later. And you can, if you want, design some helper chips, chips that we haven't specified, which will act like private methods in high-level programming. However, this is really not necessary, and we advise that you don't do it. There's no need to invent any new chips. Just use the chips that we provided, and you should be fine in completing this project. And in general, just like we always do in computer science, strive to use as few parts as possible. Try to create an implementation which is elegant, readable, and well done. Now, I'd like to end this unit with a few notes about frequently asked problems and questions that students raised when working on Project 1. Well, first of all, you have to realize that when you create your HDL program, you have to use some external text editor like Notepad or whatever editor of your liking. You cannot create HDL code using our tools. In particular, you cannot write code inside the simulator. Once again, do it in an external editor, and once you save your HDL file, you can load it into our simulator. The next point that confused some students is that you cannot use a chip as a chip part in its own implementation. There's no recursion in HDL. All right, so all the chips that you use when implementing a new chip have to be some other chips that you've implemented before or some built-in chips which are always available as well. Now, when you run your HDL in the simulator, if everything works well, you will get a message at the bottom left of the simulation saying something like simulation completed successfully. If something goes wrong, and if there's a syntax problem with your HDL code or anything like that, you will get an error message printed in red. So once again, some students tended to miss these messages. So pay attention to the to the bottom left of the simulator when you simulate your chips. Now, in Unit 1.6, Noam explained the whole notion of multi-bit buses. And one thing that we would like to add to this discussion is that these buses are indexed from right to left. So if A is a 16-bit bus, then A0 stands for the rightmost bit, sometimes called the least significant bit or the LSB. And A15 stands for the leftmost bit, also called the most significant bit or the MSB. So this is just a convention that you have to keep in mind when you index your multi-bit buses. And finally, we want to emphasize once again that we provide all sorts of resources with which you can consult when you write HDL code. In particular, the book has a whole appendix dedicated to HDL programming, and this appendix is also available online in the NAND to Tetris website. And there's an excellent document called HDL Survival Guide, which was written by Mark Armbrust, and this is the first place that you have to go to when you get stuck with something and you need some advice. So this has been the end of our unit about Project 1 overview, and we are ready to go on to the last unit of this week, in which we're going to say to talk about some general observations about elementary logic gates.